Let's discuss an integration technique called integration by parts. And you have to be careful because I've seen a lot of people, when it's supposed to be substitution, will try by parts and vice versa. So perhaps we will begin with two integrals that are substitution. So they're ones we can do right now, but then I'll change one of them just a little, and it won't be something we can do by substitution. And this will motivate, I hope, the technique of integration by parts. So the first one we could do, for example, x squared sine of x cubed dx. And then we will also do the integral of maybe x e to the x squared dx. Okay, now both of these are substitution. Both of these, hopefully we see substitution, or if not, let's discuss why. Well, because here is an inside function and we have a multiple of its derivative in the integrand. Here is my inside function, a multiple of its derivative in the integrand. Okay, so this suggests substitution. We have u is x cubed, the inside function, du 3x squared dx. In my integral, handed to me as a x squared dx, which is a 1 over 3 du. Okay, so now I would like to, maybe I'll put a box around this. I want to integrate this function, and it's an integral of, let's see, sine u times 1/3 du. We integrate with respect to u. We get 1/3 times the negative cosine. Then we go back here using this to our original variable, which is x. So we have negative 1/3 cosine of x cubed, cubed plus c. And I have to move this line over like this, okay? So here is number one, right? Now, this is very similar. We see this inside function. It's up inside the exponent of e. We see a multiple of its derivative. This also substitution, okay? So we have u x squared du 2x dx. We have x dx, which is 1/2 du. Okay, now, I will say this is part of showing your work, which is quite important, whether it's on a quiz or exam or anything like this. Writing u, du, the steps. Okay, so now we have an integral. We have e to the u times 1/2 du, which is, well, when you integrate e to the u, it's just e to the u plus c. Then we have the 1/2 in front. So we get 1/2 e to the x squared plus c. Okay, great. It's a nice, well, you could even take it as review from last time. Okay, but let me change this one over here a little bit. So instead of having, I will put this line here. Instead of having x e to the x squared, I'm going to change it just slightly, the integrand. Now I'm going to have an integral of x e to the minus x dx. Okay, they almost look the same. They both have an x times e to something. Now, this will not work with substitution. With substitution. Well, just this part. For example, if there was no x times it, this we could do based on our discussion last time. Maybe I'll write what we said at the very end of that video. we talked about things like this, where a is a number, and this was 1 over a e to the ax plus c. In this case, a is -1, and so we can integrate just e to the minus x dx. It's negative e to the minus x, like this. Okay, that's fine. But with an x times that, we don't know what to do yet. And it's not a substitution, okay? So what we'd like to discuss or move toward is another technique called integration by parts. And it's very useful when you see things like this, which are a product of two functions, but it's not an obvious substitution like this one, okay? Substitution, which I didn't start from the beginning in our review of substitution video. I just sort of started doing it and reminded you because it's really something that you would have seen before, and it was a review lesson, right? This is not something you've seen before, at least that's not what I'm assuming. So let's talk about where this comes from. And substitution, as you would have learned in Calc 1, for example, it undoes the chain rule. Well, this one undoes the product rule. If we take the derivative of a product, well, this is the first times derivative of the second plus the second times derivative of the first. And I almost ran out of room. This is the product rule that you learn in Calc 1, and we use throughout. You use it Calc 1, Calc 2, Calc 3. We're always taking derivatives at different times of the semester. If I take the exact same statement and I write it by integrating both sides, okay. Integrating, what do we have? Well, what happens when you integrate a derivative? That's this. Well, integrate a derivative, we know that's the original function. Okay, plus c, but I'll take care of the plus c in a minute. This would be, now I'm just going to integrate f of x, g prime of x, dx, plus the integral g of x, f prime of x, dx. Okay? I'll show you what I'm solving for, and then I'm going to change my letters just because of the convention that we usually see by parts. So I will solve for this. Okay, and at the same time, I will let, maybe I'll do this in black, I will let u be f of x and v be g of x, okay? And then this, which I'm solving for, it says the integral of u. Well, g prime of x dx is dv. This would equal, okay, it's what's over here. This is u times v. And then I have to pull this term over to the other side if I solve for what's underlined in red. And this would be a minus the integral of v du, because if u is f of x, du is f prime of x dx, right? This is very much like when we were doing substitution, you calculate du, right? And this is the formula that people are used to seeing, looking at, is with these particular letters. This is integration by parts. So this is by parts. And you see it came from exactly the product rule. All I did was just write the corresponding, or what this product rule says in terms of antiderivatives, and then I just changed my notation a little to have u and v, okay? This is by parts. Okay, now, well, I still want to think about this, but I'm going to erase it a moment because we will come back to x e to the minus x, because before I do, what do you use by parts for? Well, just like I erased, when you have a product, but it's not every product. So I would first look at a product if you're handed a product and ask yourself, do you see a substitution. And I mean one that just jumps out at you. You see an inside function, you see a multiple of its derivative. Then don't use by parts, okay? But those were the first two examples we did, right? But if you look at a product like the one I just erased, and you don't see a substitution, but it's two functions multiplied, naturally I would think by parts, because well, here you see it's like a product and then you write in some other things, but also in your mind should say by parts, product rule. They kind of should be in your mind as being not the same operation, but complementary operations. Okay, now there is a acronym that I teach for finding u. For finding u. How do we find u? Where are you? Here I am. Well, I mean the u versus v, because what's going to happen is one, you will see a product. One of the functions will be u, or you typically see a product. We'll do an example or two when you don't. Everything else in your integral, including the dx, becomes dv. So we go in this order. This stands for logs. This stands for inverse trig. This stands for algebraic. Algebraic is something it's like polynomial, or you could have square root of a polynomial, that kind of thing. That's the algebraic. Then you have trig, and then you have exponential. And this is the order in which you go. Okay, I could write trigonometric, but in any case, it's fine. So you go in this order looking for u. Do you have a log? Do you have an inverse trig? You keep going in this way until you hit something in your integral. Circle it, you have it, that's your u. Everything else is dv. And then, well, you see everything we need. We need u, v, we need v and du. Then we jump into the formula for integration by parts. Okay, so let me, now that I have talked about Liate, let's go back to the one that I erased just moments ago, which was x e to the minus x, and we will find an antiderivative for that using by parts. Okay. Here. So we have an integral, x e to the minus x dx. Well, let's go in order. Ask yourself, do we have a log? No, we don't. Do we have inverse trig? No, we don't. Do we have algebraic? Yes, we do, because here, this is algebraic. You're looking for something polynomial, maybe square root of polynomial. Okay, so this is going to be our u. Let's set it up. So here is the kind of little side work box I make for by parts. U is x, dv is everything else. So this is going to be e to the minus x dx. Now, make sure when you are writing out u and dv that when you multiply u times dv, you see your entire integrand, except without the integral sign. So you should see all of this. That way you know you have everything. Then we need du and we need v. Okay? So this way we differentiate, this way we integrate. Du is dx, and v, well, I erased it down here, but we did this at the very start. This is minus e to the minus x. Okay, we don't really need the plus c. That will come at the very end. Well, we don't need the plus c, I would say, in our side work box. Okay, then it's uv minus the integral of v du. And I always draw the little arrows because it gets me going on the right path. So this is uv minus x e to the minus x minus the integral of minus e to the minus x dx, like this. So this was, maybe because I don't have my formula up anymore, I will write it this first time. This was Well, it's uv minus the integral of v du. And you really multiply this way, like this. Okay, so now what you see, this integral is something I can integrate now. I don't need to. This was something that, well, I look at it, not sure. We don't have an antiderivative just off the top of our head. This one, on the other hand, we do, right? So this is minus x e to the minus x. This, well, let's think about the SIGN sign. This is a plus. When we integrate e to the minus x, we get another minus. So this will be a minus. And then plus c. So this would be our antiderivative here. Maybe I will do another one over here. Okay, this is integration by parts. So let's do another one. We have the integral x squared ln x dx. Okay, well, if we go through this, liate, maybe I should write it for this one because we have a different order here. Liate. Do we have a log? Well, immediately we do, right? So we stop here. This says my u will be ln x, and dv will be everything else, which is x squared dx. And again, check. Make sure when you multiply u times dv that you have your whole thing except the integral sign. And in fact, I do. I have x squared ln x dx, right? Then here we differentiate 1 over x dx. Here we integrate x cubed over 3, okay? And then here comes by parts. It's uv minus the integral of v du. Okay, so we will go back to black for this. Okay, so this is x cubed over 3 ln x minus the integral x cubed over 3x dx. Well, now, you see, I can integrate this, but I have to simplify it first. So this is x cubed over 3 ln x minus the integral x squared over 3 dx. And now when you integrate, it's going to be a cubed power again. It's going to be an x cubed, but now we have over 9 plus c, like this. So this is my antiderivative here. Now let's do this one, which is going to be exciting. It's the integral of x squared cosine x. I give myself a little bit more space, as we will see in a moment that we need. Well, it begins looking just like any other one that we have done so far. We see a product. It's not an obvious substitution. And if we go in order, there's no log, no inverse trig, but we have algebraic, which is the x squared. Okay? So my u is x squared. dv is everything else. Okay. Then we differentiate 2x dx, and here we integrate. We get the sign uv minus the integral of v du. Okay, here we go. So this integral is, well, it's x squared sine x minus the integral of 2x sine x dx. Oops, almost forgot my x. 2x sine x dx. Very good. Well, okay, you see here, this is not something we can just immediately write an antiderivative for. Unlike the last few, we see another product. We have one function times another, not an obvious substitution. So in this example, and sometimes this happens, we have to do integration by parts a second time. Okay. So now, maybe let's underline in red here. This is my integrand. So this was time number 1, and then here I will do time number 2. This was time number 1, time number 2. Okay. Well, it's the same is the A, liate, because we have algebraic. It's 2x. So I was doing these in blue. Sorry about that. U is 2x. dv is everything else. Sine x dx. Okay. Now I differentiate. I differentiate here. du. This is 2 dx. And here I integrate. When I integrate sine, negative cosine. Okay. Then maybe I will draw back my red line. Okay, and then it is uv minus the integral of v du, like this. Okay, but we can't forget this first term, and this minus sign we can't forget. We can't forget to distribute it. This is something that I see happen a lot. Well, I'll just say it's an easy mistake, as you'll see in a moment. Minus, well, here we go. Parentheses, we have minus 2x cosine x, and then minus the integral of minus 2 cosine x dx. Okay, just enough space. Well, it's just a constant times the cosine. Definitely we can integrate that. So now we're ready for our last step. These two negatives become plus. And then now we have to, this is the part where it's easy to mistake your SIGN, because you see this is a plus, and when you integrate cosine you get the positive sign, but there's this minus out here, and it's really easy to forget to distribute it, to just drop it or something like this. But anytime, of course, you have a minus and there's a sum, distribute. So don't forget it. So it's 1, 2, 3 negatives, makes negative. We integrate cosine. Well, we get 2 sine and then plus c. So this here is our final answer, where we use integration by parts 2 times in this problem. Let's do something where we have a definite integral maybe. Let's go from 1 to e of just ln x dx. Here's a definite integral. Now you might be saying, how weird, or what are you doing? I don't see a product, and you mentioned by parts and product rule going hand in hand. This one's a little bit deceiving because you don't see a product, but ask yourself, do you know an antiderivative for natural log? I don't. It's not one of the ones that I know things about, that I just keep memorized in my head. Certainly I know the derivative of natural log, but not an antiderivative. So this one, in fact, is by parts. And similarly, another one you could do by parts that would also be similar is just the integral of the tan inverse. This might be in your homework, for example. I don't remember exactly. But if you see just an inverse trig, tan inverse or sine inverse, or just a log, by parts is good for this. So, okay, we will still go in the order of liate. Okay, here u is, well, the very first thing. We have a log, ln x. And then dv is everything else, which in this case is just dx. Okay, now differentiate du, 1 over x, dx, integrate, it's x. Okay, and then we have uv minus the integral v du, like this. except it's definite. So one thing you could do is you could come to the side, calculate an antiderivative, but I will just, work with the fact that I have upper and lower limits of integration in the problem. So this is going to be x ln x, and then evaluated 1 to e, like this. Then subtract the integral from 1 to e of x over, well, x times 1 over x dx, like this. And then, okay, I will evaluate here. It's e ln e minus 1 ln 1. And then minus here, this is just the integral of 1, right? I integrate, I get x, so this is x evaluated, just this, between 1 and e. Now, natural log of 1 is 0. Natural log of e is 1. So I get e, and then I have minus here. This is e minus 1. Oh, goodness, I just get 1. Well, that's interesting. What this says, as we know, if you graph natural log, here's 1, out here is e. The natural log goes through the point 0, 1, and then here. This says that this area under the curve between 1 and e, here, that this area is 1. Okay, quite fascinating. The e parts canceled off. Okay, let's see. Let's do one more, and then we will be done. This one is going to involve a little trick, and it is good to see. So we'll do one more example of by parts. I do have an example video with a few of like exercises for by parts, so I will put it at the end. So you can click on if you want to see a few more examples. So let's do this. Let's do e to the x cosine x dx. This one is kind of exciting, I think. Now, if we follow this order, we do not have log, inverse, trig, algebraic. Oh, we have trig. So we had to go all the way to the t here, which is okay. So this suggests we have u is the cosine, and dv will be everything else, e to the x dx. Okay, then we differentiate du, negative sign, dx, can't forget that, v is just e to the x, and then uv minus the integral of v du. Here we go. So this equals, we have uv minus the integral of v du. Oh, but there's a minus. Minus. Like this. Well, maybe I will take the step because and just turn this into a plus, just to make my life easier for the moment, although I don't have to. I could have worked with it with 2 minus signs. Well, this, you see, this is a problem at the moment because this is not something that we just have an antiderivative of that we can work through, or we can't use properties of exponents to simplify this in a way we can integrate. So let's do this again. Now, again, look, we have an e to the x times a trig function. This is the t in Liate, so my u will be the sine, and dv will be e to the x dx. We differentiate the sine, du is cosine x dx. We integrate this, we get e to the x, and it's uv minus the integral v du. Okay, so this is, well, we have to copy this part down, okay? We recopy. Now, this integral, it is e to the x sine x minus the integral e to the x cosine x dx. Well, you might be thinking you did something wrong, or maybe you think I didn't do anything wrong, but you see this and you say, oh, do it again, or we're going to be doing this forever. Okay, look, we have e to the x cosine x. This is what we were trying to find in the first place. Maybe it looks like we're never going to find it because we're just going to keep by parts, over and over and over. However, let me erase some of this so I can write it all on one line. Okay, so you see we have worked out 1, 2 by parts. We are down this integral equals this sum of terms. So let me just erase so I can fit everything together. And we will look at what we have. Okay, so I'm just moving this up here. This is e to the x cosine x plus e to the x sine x minus the integral e to the x cosine x dx. Okay, and I'll even erase this part. This was our work. I mean, if you're working this out on a piece of paper, don't erase and only turn in this, right? Just write it underneath. Okay, well, look what you can do. Don't do by parts again. We have this. We can move it over to this side and it becomes positive. So what will happen here, if I take this, which I'm trying to solve for, move it over to this side, I will have the following. I have 2 integral e to the x cosine x dx, and this will be e to the x cosine x plus e to the x sine x. So now if I want to solve for this, I have 2 times some 2 times this, it's not a number, it's an indefinite integral, but 2 times this is equal to this. So to solve for this, you just divide by 2. So we have this integral, and this is the trick I mentioned. This is a fun one. It's a half times this, cosine x plus e to the x sine x, except, don't forget, plus c. And then this is this antiderivative. It looked like by parts was not going to end, but we were able to bring this on this side. We have 2 times the quantity we're trying to solve for is this expression, and then we just divide by 2. Okay, so now if you look over here, you can see the example video. You can see a few more examples of by parts, or you can start working problems and come back to this video after you've attempted some. Okay, right here.